Excellent. Some more integration then. But before I do, thank you so much to the person who pointed out the giant mathematical blunder that I made in yesterday's video when I was doing this integral. I don't remember what number it is, but I claimed that if I made the substitution u equals e to the x, that when I differentiate that, I get du equals equals e to the x dx, and then I claimed that this e to the x cancels with this one. But I'm being an idiot here, right? I just wasn't thinking it through, made a mistake. We all make mistakes, all human. This makes 1 over e to the x, which then causes this, when you replace that 1 e to the x into there, that makes 2 of them there before you can put your du. And this is seems okay because you can then say this is u squared maybe here. You can say this is u squared here and then a u squared here. And maybe this has potential. But it's certainly not what I said it was. Maybe this has potential. I'm not really sure. There's actually a really sneaky way you can fix this pretty much immediately, and it's by thinking about it's by trying to force the thing that I claimed in the first place, right? Like what I was trying to do was cancel this e to the x with the one I get from the substitution. So how can I force that to happen? Well, it's by using a slightly more intelligent substitution, e to the minus x, because then the derivative is this, and when you times both sides, then this over here does become e to the x. When you times both sides by e to the x, you can get this here. And so this does cancel with this now, which is perfect. The price that you pay, of course, is, well, not that. The price that you pay, of course, is a minus here, which obviously doesn't make a difference. But also, e to the 2x is now, well, it's going to be 1 over u squared, right? Or u to the minus 2. So this is the price that we pay here. And again, maybe we could have got to this by factorizing out from what I said previously. Maybe that ends up being the same thing. I'm not sure. But in any case, I think I can do this from here, because what I can say is, if I group this together, right, put this minus 9 in here, I can say this is minus 9 u squared. And now root the fraction separately, root this, root that makes root u. Sorry, that makes u just on the bottom here, because root u squared is u. Flick that u up to the top, you get 9u. So it ends up being something that looks like this, and then this is the only thing on the bottom. And now some of you might recognize this. This is now, I think, fairly nice. I'm going to copy this bit because I'm going to need it. And then it's going to be 9u into what I just copied to the power minus a half. And you might recognize this as something that we've seen a few times, reverse chain rule. And we'll actually get the correct answer, I think, which is, well, this 9 is already doing good work because this would make 18u derived. Times by half is just 9u. So I think I can just straight up get rid of that and add this in there. And I think is, and then that minus is there, but then the minus from this derivative cancels, right? So I think this might just be it. Yeah, that looks all correct to me. So yeah, just thought I'd do that. Thank you so much to the person who pointed that out. Now let's get on to some proper integrating. I also just realized that I forgot to put the substitution back, having just done that. But the one that I just did, you put the substitution back and then you're good to go. Okay, so let's get into some actual live integration then, because that's what we said we would do. 217, it keeps picking low ones for me. Hopefully we'll get a high one. Oh, this is not the right booklet, is it? Oh, it doesn't really matter, does it? This is the condensed one, it looks like. Is it the same booklet? I want to make sure it is the same booklet. It's the same booklet, right? Why is it all... What? In student version condensed... Oh, student version condensed, okay. Sure. 217, sorry. 217. Sorry for being confused there. Just an old man. Right, cos of log of x over x. This looks fun. So let's break it out. So it's integral of cos of x. No, sorry, it was cos of, in brackets, log of x, right? I don't think it was cos of x log of x, but I will check, of course. And then how do I put this bracket here? There. Is that all good to go? I hope it's all good to go. It's all good to go. Okay. Now, the first thing I'm thinking immediately upon seeing this is that over x, I could write as 1 over x, like this. And the reason I'm thinking that, of course, is because the derivative of log of x is 1 over x. So now I have the derivative sitting here. The problem is that doesn't quite work, because like the derivative of cos of f of x, if we just write it here, cos of f of x derives, let's just say d by dx here, not just to, it doesn't matter, that'll be fine, derives to f dashed of x, which is what I've got there. But then there's also going to be, it's going to change right to sine, I think, which is going to be a bit of an issue. Or will it be an issue? Can I not just say this integrates, does this not just integrate to sine of log of x with a minus? Would that not work? Because, yeah, right? Because log derives to 1 over x, and then cos derives to minus sine, and I think that's just fine. So yeah, that's the first one, I think, done. So yeah, we'll grab another one and proceed. 402 is the number. Again, I hope we recognize any repeats, because it's getting to the point where, oh my gosh, what is this? Okay, cool. This looks interesting. The integral of. Yeah, this is, apologies for how many times I'm going to have to flick back and forth here, because that did not look very straightforward to write. It was 1 minus cos x right at the front. And then someone pointed out as well that I typed one of these wrong in the last video, despite double checking, just being blind. 1 plus cos x all squared into plus sine squared. Okay, so clearly there's going to be a cos squared plus sine squared in here, which is fun inside this bracket. So that's the first thing maybe we should just immediately be going for here, is when we expand this out, we end up with, in here, we're going to get 1 plus 2 cos x. And then plus cos squared plus sine squared is 1. So that's 2 plus, let's go, there's 2 plus 2 cos x is going to be here. Okay. So that is that, I think, good to go. So now what on earth do we do to try and sort this out? Well, this, am I being silly? Is that not? Okay, so cos squared, no, cos of 2x is cos squared x minus sine squared x. I'm taking quite a big leap here, because I don't actually know whether this is going to be helpful, but this looks, okay, so basically what I'm thinking is I can do this, right? I'm just going to write x over 2, because it's neater. I can do this, right? Because the double angle formula still holds. Now, if I then say sine squared is obviously 1 minus cos squared, this becomes 2 there and a 1 here. And what I'm thinking about here is, does this cancel stuff? It does, right? Because if you double this, you're going to get 4 of those guys there. Oh, fantastic. Absolutely nailed it. Absolutely nailed it, hopefully. So 2 cos x is going to be all of this. Minus 2 means it's just this. Yeah, fantastic. So the root of that is obviously just 2 cos of x over 2. And now this still isn't trivial, right? This still isn't trivial. I'm going to put the 2 over here. This still isn't trivial, because we've still got this cos x over 2 in here, and x over 2 and x don't really play well together. So we're still going to have to think about this a little bit. Could I do the same trick here and make this into... Can I not just, if I halve that back down? Yeah, this will work, right? The ones cancel. Oh my god, this is so nice. The ones cancel, so we end up with this there, which is the integral of cos cubed x over 2 with a 4 here. And now all we have to do is integrate integrate cos cubed. Ooh, sorry, PowerPoint not doing well there. Anyway, now we have to integrate cos cubed. Okay, so there's a bunch of ways we could think about doing this. I think what I'm going to say is that I'm actually going to go back a step, and I'm going to go back to here, because I think I can play the usual trick, which is well worth knowing here, which is that this is sine squared into x over 2. Close another bracket. And the reason that this is good is, and I'll still put this 2 over there. The reason that this is good is because when you expand that out, you get cos of x over 2, which is obviously super easy to integrate, minus sine squared of x over 2 into or times cos of x over 2. And what I've created here is I've created obviously something that's super easy to integrate at the front, but this here is just something of the form f of x to the power 2 or whatever times f dashed of x, right? So I think clearly cos of x over 2 integrates to a half, or integrates straight to a half sine of x minus over 2. Here, what am I doing? Sine differentiates straight to cos, you absolute muppet. Amazing stuff. Amazing stuff, sir. That was incredible. Anyway, cos integrates straight to sine, you muppet. And then we're going to have sine cubed here. And then we're just going to have to account for the over 2 business and possibly any negatives. There aren't going to be negatives because sine differentiate to cos, but there is going to be a 1/6, nope, 2/3, because you times by 3, then half, which gives you a 1. And I think that will be, pretty much that done. Cool. Anyway, I'm glad that I fixed the first question as well. We've got time for another, so let's do another. Oh, don't want to press that. Got time for another. 495. These numbers ring so many bells, but did we do this one? This 16 plus 9 thing. Have we done that? Maybe we have. I think on the basis that I'm saying maybe we have, we probably haven't. I mean, you'd think I've only done like 10 of these. Oh, it's moved. We've only done like 10 of these. You'd think that I would remember every one that we've done. Sine of x over 9 plus. Okay, I don't think we have done this one. No, 16 plus 9 cos squared of x. Ooh, of x. Okay, dx, I presume. Let's double check. Yes. Okay. Right. Okay, so first thing to say, the top is not just the derivative of the bottom, because this derives to 9 cos sine, which isn't quite this. If you could force a cos in there, that would be amazing. Yeah, that would just be terrific stuff. So, like, you could think about, could you just times it by cos over cos, but that, of course, completely messes up the derivative of the thing on the bottom, so that doesn't work at all. So yeah, no, that's no-go. Could you write this? I mean, does making this 1 minus sine squared help? Almost certainly not. 16 plus 9. Well, does it? I mean, it makes it. The thing about making this 1 minus sine squared, I don't know why I copied that again, is that you at least end up with that should be a 9, of course. You at least end up with a difference of 2 squares, right? On the bottom, which is certainly interesting. I don't know whether it's helpful, but it's worth thinking about whether or not we could write this. Sorry, that should be a plus first. Whether we could write this as partial fractions in some way. Now, it's also worth thinking about before we start that process, whether or not that would be helpful. Because, okay, let's imagine that we had this in 2 fractions. Like, is it even helpful that I've done that? Can I integrate things of the form 1 over 5 plus 3 sine x and so on? Or k over that thing? Is that, I don't even know. Surely there's some way for me to do that. Making some kind of substitution or something surely would work. It seems like it would make, so, okay, let's just see. So sine x, is it just going to be, it's actually going to work. So if I just say it's a into the first one, or the second one, it obviously doesn't matter, plus b. Like, does this even work? I mean, I don't think I've ever broken up something like this into partial fractions, or at least I haven't for a long time. So I actually can't remember whether this works. Obviously, we need this order balance, which means we would need a to be minus b. Otherwise, that's not going to work. And then we end up with, oh, sorry, that should also be an a. And then we just need minus 3a minus another 3a to be 1 sine x over there. Okay, so that's kind of worked. So I think this is the integral of, I've messed this up so much. A is minus a sixth, and A was the one above this one here. So I think it's, and I guess it's not going to be too hard to check this, but I think it's going to be a sixth into, this one needs to come second with a minus. I think it's this. Let me just check this. So you end up with 5 minus 5 is fine, and you end up with 3 minus minus 3 is 6 sine x's. So yeah, this works fine. So now we come back to this question that I was asking myself before, which is, do I know how to integrate stuff that looks like this? And the answer is I'm not sure. I'm legit not sure whether I know how to integrate objects like this. It feels like I should know, because how hard can that really be? I'll get rid of the brackets because they're annoying me a little bit while I pause and think about this just for a second. Okay, so this is posing an interesting question. Substitutions wouldn't work here, would it? Because I mean, basically, I only need, if I leave this here, um, I only need to think of one of these at a time, because obviously, if I can figure out, if I remove all the fluff because I don't care about it, if I can figure out how to do one of these two things, the other one I can just do. Like it's not going to be any different. So I just need to figure out a way of doing one of these two, and then I'll be fine. So, okay, I had some thoughts, and most of those thoughts have gone now, because let's think about a substitution, because why not? Like I don't think it's going to work. It usually doesn't in cases like this, but let's just think about it. So du is cos x dx. So you'd end up with 1 over, and then this cos of x is going to be annoying, right? Like, because this is the problem with doing this kind of thing. You end up with a 1 over cos of x. This is going to be a u, which is fine. But you'd end up with a cos of x here, down here below. And I guess you could write cos of x as root 1 minus u squared, because it's, of course, root 1 minus sine squared. But this, I mean, this doesn't look good. This just doesn't look fun. I wouldn't have said. However, it's making me think maybe there are interesting ways around this. What if you did this sort of thing? Because this minus 3 obviously is fluff, it doesn't matter. You could replace all of this, therefore, with u. And then you'd end up with a minus 1/3, obviously, doesn't make a difference. And then you're still dividing by cos of x. Now, cos of x is slightly more confusing in this case, isn't it, actually? So maybe this is why this maybe not be a good idea. It's u minus 5, or it's 5 minus u, actually, over 3. It's PowerPoint. Go in there. No, in there. Thank you. And then we square all of that. And then it's 1 minus all of that squared. Is that... I mean, I'm still not completely... It might work. I don't think it will. Let me leave this in brackets, of course. And then that's 1 minus cos squared. So the thing that I was looking for, which is cos, is 1 minus all of this square rooted, and that needs to be on the bottom here. But this is just a mess, right? Like, it's 1 minus all of this, but all of that is to the power of a half. What I was hoping for was some kind of inverse chain rule to just appear with this u on top, but it just doesn't work. So I think I'm going to abandon that plan as well. So okay, Any more ideas at all? T formulas. Do we just go back to that bad boy? T equals tan x over 2. I know I always just go back to this when I don't know what to do, but I don't know what to do, so you can't blame me. I just don't know what to do. I'm just not good enough. People who are better than me have already answered this question, but yeah. Then we have dx equals, now what was it? Was it 2 over 1 plus t squared? I think it was. I think that's it. Um, yeah, let's say that that's it. So this becomes 1 over. So this thing goes in here. I mean, we may as well write a 6 here, right? And then this thing goes in here. Ooh, this thing goes in here. Okay, so what we could obviously do here is we could say that this fraction, if I maybe put this in brackets just to be clear about what I'm about to do. So this fraction here can be written as, well, this one here is 5 plus 5t squared over 1 plus 1t squared. So this is 5 plus 5t squared plus 6t. And now this denominator here cancels with this one here. So we end up with a 2 outside from this 2. So that goes away now. And this all cancels with this down here, like so. And so now, of course, this can go away. And this denominator here just becomes, sure, I'll just type the t myself, becomes this. Now, I do know that I can integrate things look like this, which is good, because that's really good, because I can now answer the question. So where did this minus go out of interest? Was this minus here? That should have been minus. The reason that I spotted that is because I think that the only difference with this one is it's gonna have the plus here instead, because the 6t bit came from that there. So I think what I can do, if I just get rid of all this, is this thing here is gonna become, I'm gonna put the 2 back here for a second, is gonna become that integral dt minus, and then I'll just copy the whole thing. There's still a 1/6 out here, which I may as well just do this with, because, you know, that's obviously what I should do. And this can become a 1 as well. But this one should have a plus there, I think. And I think that's literally the only change that I need to make. Now, this is good. I'm going to write this in the more normal way. Just bear with me. Now, the way that we do these sorts of integrals is we can complete the square and try and get it to look like something that's in the formula book. Now, that's not going to be so easy because of this 1/5 here. Should we just take out a fifth from both, just so that completing the square is made nice and easy? I mean, the 6/5 will be a bit annoying, but whatever. And now completing the square is going to be nice and easy for both. So this is going to be, and they're going to look very similar, of course. I might do some copy pasting here. This is going to be 6 minus, now 6/5 of is 6/10, which is 3/5, I think. Let me just check through to 6. Yeah, that's all fine. And then taking away square, that's take away 9 over 25, which we're then going to add 1 to, which I think makes plus 16 over 25. And this is going to be the same, except Control C. That's going to go there, right? And now this is when we say, okay, this is of the form. Now, just imagine in your heads, I'm not going to write it down, that we make the substitution here, u equals t minus 3/5. That should be a plus. And likewise over here, u equals t plus 3/5. That's a linear transformation, and so du would be dv, so that's dt, so that doesn't change. All that really matters is this. By the way, I'm only going to do this to 1, but I could write this as 4/5 squared. And the reason I'm going to do that, of course, is because this is now of the form something squared, which is the variable, plus something else squared. And I pre-prepared this time my A-level formula book. I should have already got it to the page that I actually need, because there's obviously only one page here that I do need, which is this one. Might make a mental note that it's page 16. Anyway, it's this here, right? or at least actually, it's weird, right? Because one of them is this here. One of them is a squared plus x squared. That's no, they both are. They both are because they're both plus ones at the end. Yeah, they both are. That's fine. So okay, they're both this form here. So I think we've got two different arctans going on here. We've got a 15th of arc. Oh, so by the way, the A is 4/5. So it's going to be arctan of, and now, like I said, the A is 4/5. So what's the actual formula? So it's 1 over 4/5, which is 5/4. The 5 cancels here, so that I think makes it 12, I believe. And the x over 4/5 is 5/4 x. So I think that's the first one. Have I missed anything? I have missed something, because of course this is the x here. So I think that's 5/4 into t minus 3/5. And the second one is going to be identical, right? Except it's going to be t plus 4/5, 3/5 here instead. So I think this is something like, and then of course there's a plus here. So I think this is, I'll make it a bit smaller. So I think this is it, unless I'm horribly mistaken, which someone undoubtedly will point out if I am. And yeah, all I need to do now is say t was tan x over 2. So this is arctan of tan x over 2. There's almost certainly a nicer way of writing this. The fact that there's arctans and tans here means that there was a nice way of doing this, and that there's some cancelling going to go on, which I can't bother to do because this is definitely integrated. So I'll maybe make this all a bit smaller so we can answer. But this is the answer that I have here. I'm not going to be so bold as to claim it's definitely the right answer, but I think I had the right ideas at least. I think I made some progress and at least got out the right ideas at some point. So if there's some numeracy mistakes, hopefully I haven't made a giant mathematical blunder like the previous video. But hopefully all the ideas were correct and pointed out to me if not. Anyway, thanks for watching. I'll see you next time.